Imagine I give you a level of Super Mario Bros. And ask you a simple question. Is it possible to reach the flag? Is there some sequence of button presses that takes Mario from the start of the level to the end? In the regular game, the question is trivial. But if we allow for custom levels and without any limits to the size, things get more complicated. Now we are asking whether any possible configuration of the game's elements has a solution. And that turns out to be surprisingly difficult to answer, not just for humans but for computers too. In fact, it is the same kind of hard as problems related to designing new medicines, optimizing delivery routes, or cracking encrypted messages. I know it sounds absurd, but the connection is real, and we can literally prove it. Along the way, we're going to explore one of the most famous open problems in computer science, a problem with a $1 million prize still waiting for anyone who can crack it, and one that's genuinely easy to grasp, even if solving it might be another story. Complexity theorists have been organizing problems into classes for decades. What they care about is understanding how our solutions scale as the input gets larger. Computers are getting faster at an exponential rate, but if a problem grows faster than that, we'll never catch up. Some problems already have very efficient solutions. Sorting a list of names alphabetically might take time for a human, but for a modern computer, even a long list is no problem. Others are on the opposite end of the spectrum. Take playing a perfect game of chess, for example. The number of possible moves and positions grows so quickly that even a standard game is beyond what any computer can solve, today or in the foreseeable future. Even verifying whether a single move is optimal is something we don't know how to do. But there's also a middle ground. Some problems are hard to solve, but easy to check once you have a solution. One example is Sudoku. Solving the regular 9x9 puzzle is simple for computers, but as the grid gets larger, they start to struggle, and pretty fast. Still, no matter the size, verifying a solution just means checking that each digit appears in every row, column, and box. That's quick and easy. Now we are getting close to the $1 million question. Computer scientists have names for these categories. If a problem has a known efficient algorithm, technically speaking one that scales polynomially with input size, it belongs to a class called P. If we don't know how to solve it quickly, but we can verify a solution efficiently, it falls into NP. P includes things like checking if a number is prime or finding the shortest path on a map. NP includes problems like packing items into limited space or designing complex circuitry. These are just a few examples. Both classes are full of problems from science, engineering, logistics, finance, games, and more. And around them, there's an entire zoo of other classes, including ones that capture things like chess and our Mario problem. But that picture can change, because it all hinges on the algorithms we've discovered so far. Some problems that were once in NP have moved into P, because someone found a clever new way to solve them. And this has happened many times. So that leads to the natural question. Could every NP problem eventually turn out to be in P? If we can verify solutions quickly, does that mean there's always a fast way to find them? That's the big one. In other words, does P equal NP? Most researchers think the answer is no, that some problems are inherently difficult to solve, even if their solutions are easy to check. But the truth is, we simply do not know. And that uncertainty sits at the core of one of the deepest unsolved problems in computer science. Why? Let's talk about Mario. We're going to see that deciding whether Mario can reach the flag on increasingly large levels is at least as difficult as any problem in NP. In other words, if you could solve this one problem, then you'd effectively be able to solve all problems in NP. That makes the Mario problem what we call NP hard. To prove it, we'll take a known NP hard problem and turn it into a Mario level. And I don't mean that metaphorically. Any instance of that problem can be rephrased as a stage built from Mario's rules and pieces. So if you had a way to tell whether Mario can reach the end, you'd also be solving the original problem. And by extension, every problem in NP. This technique of turning one problem into another is called reduction. The problem we are going to reduce to Super Mario Bros. Is called 3SAT, short for 3 satisfiability. It sits right at the intersection of NP-hard and NP, meaning it's as hard as any NP problem, but its solutions can still be verified quickly. Problems like this are called NP-complete, and they are especially interesting because they represent all of NP while being just as simple, or, well, not harder at least. The 3-SAT problem goes like this. You have variables, say x, y, and z. Each can be true or false, and they can appear plain or negated, like x or not x. In 3-SAT, we group 3 of these into a clause, connected by OR, for example, not x or y or z. A clause is true if at least one part is true. We then build an expression by combining several clauses with AND, meaning they all need to be true at the same time. Here's a satisfiable expression. It can be true in many ways, for instance setting z to true and x and y to either value. But here's one that isn't. No matter how you assign x, y, and z, at least one clause will always end up false. The challenge is, for any given expression, can we tell if there's some combination of values that makes it true? That's the 3-SAT problem. Now here comes the clever bit. It turns out that any 3-SAT formula can be transformed into a level of Super Mario Bros. One that's winnable if and only if the formula is satisfiable. To do that, we build the level from modular pieces called gadgets, each simulating part of the formula's logic. It starts with a simple gadget that gives Mario a mushroom, meaning he'll be able to break and activate bricks, but won't fit through tight spaces. He needs to stay big until the end, because the path to the flag is blocked by a final brick. That's what forces him to grab the mushroom at the start and carry that choice through the entire level. Then come the variable gadgets. Each one presents Mario with a binary choice: drop down on the left or drop down on the right. That choice represents assigning true or false to a variable. Once he picks a side, there's no going back, and the path he falls into determines which clauses he'll be able to satisfy. Clause gadgets are next. Each has 3 entrances, one for each literal in the clause. If Mario arrives through one of them, he can activate a block to release an invincibility star into a sealed-off area. He can't grab it yet, but later it'll be waiting. Once all variables are set, Mario faces a final stretch that runs through every clause gadget. But each one is guarded by deadly firebars, and the only way through is to collect the stars unlocked earlier. If Mario never reached the clause, meaning no literal made it true, there won't be a star to collect, and he won't survive. So unless the formula was satisfiable, he won't make it to the end. There's one last piece needed to make everything work: the crossover gadgets. They allow different paths to intersect without letting Mario switch between them. Without them, he might backtrack and assign both true and false to the same variable, which breaks the logic. The gadget might look messy, but the idea is simple. It uses Mario's size and block-breaking capabilities to control where he can go. When you arrange these gadgets in the right pattern, they simulate the logic of a 3-SAT formula, completely and faithfully. The takeaway is this: the question, is this formula satisfiable, becomes logically equivalent to, can Mario beat this level? So, we took a problem that represents all of NP and turned it into a Mario level. That means if you could write a program that decides whether any Mario level is beatable, you could use it to solve any problem in NP. The intuition is that this is a difficult problem, that there's probably no fast way to solve it. But we don't actually know that, not for sure. And if someone ever does find an efficient way to answer the question, can Mario reach the flag, then, by extension, they found an efficient way to solve every problem in NP. That would mean P equals NP. And that would shake the foundations of computer science. We'd have to reassess countless assumptions across almost every branch of science. It would break modern cryptography, but it might also genuinely help cure cancer. And that would change the world. See you next time.